Most of us walk around thinking that the world is pretty straightforward. You throw a ball, it follows one path. A planet orbits the sun, it follows one path. But what if I told you that this solid, predictable reality we see is actually a convincing illusion? Yeah, let's pull back the curtain on this quantum illusion together.
So, think about it like this. Let's say you're a lifeguard at the beach, and you see someone in trouble out in the water. You need to get to them as fast as humanly possible, right? Now, you wouldn't just run in a perfectly straight line, would you? Of course not, because you know you can run way faster on the sand than you can swim in the water. So you automatically find the perfect path. A little longer on the sand, a shorter time in the water. You find the path of least time. Well, believe it or not, a beam of light does the exact same thing. But here's the question that baffled physicists for ages. How in the world does a particle of light know the fastest route before it even starts its trip?
And here is the absolutely wild answer. It doesn't choose. It doesn't need to know. To get from point A to point B, that particle of light, or that thrown ball for that matter, it literally explores every single possible path. I'm talking about the straight path, a wacky path that loops around the moon and comes back. Literally an infinite number of paths, all happening at the exact same time. And no, this isn't just some fun thought experiment. This is how the universe actually works at its most fundamental level. It's bizarre.
Okay, so if everything is taking every path imaginable, why do we only see one, right? Why doesn't a basketball take a quick detour to Mars on its way to the hoop? Well, it all boils down to this one fundamental rule of the universe, and it's all governed by a single crucial quantity called action.
So what is action? The best way to picture it is to imagine that for every single one of those infinite paths, the particle carries a tiny spinning stopwatch. The speed of the hand on this stopwatch, that's determined by the action of that specific path. Now, for almost all of those crazy, inefficient paths, that little stopwatch hand just spins like crazy, an incredible number of times.
And here is where the magic happens. When all these paths arrive at their destination, you have to add up where all those little stopwatch hands are pointing. For almost every path, the hands are pointing in completely random directions. You add them all together, and they just cancel each other out. Poof! That's called destructive interference. But for one special path, the most efficient one, the one with the least action, all the stopwatch hands basically line up. They're all pointing in the same direction. They reinforce each other. That's constructive interference. And that is the one path that survives to become the reality we actually see.
For a long, long time, we've seen this kind of spooky behavior with tiny, massless particles of light. But a brand new breakthrough has just taken all this quantum weirdness and slammed it right into the world of things that have actual mass. And honestly, this changes everything.
Man, this quote from Dr. Sean Hodgman over at the Australian National University just sums it up perfectly. Because for the first time ever, scientists have gone way beyond the textbook. They've actually seen an atom, something with mass, entangled with itself, literally existing in multiple places at the exact same time. This is not a theory anymore, it's an observed fact.
And look, this wasn't just some minor experiment. The team used helium atoms. These are way, way heavier and more complex than photons. And they didn't just prove entanglement in some abstract internal property, they proved it in the atom's actual physical movement through space. And here's the kicker. Because these atoms have mass, they're affected by gravity. This just blew the doors wide open for a whole new way to test how the biggest force in the universe, gravity, gets along with the universe's tiniest, weirdest rules. So while we're making these mind-blowing theoretical leaps, there's a huge practical side to all this. Trying to actually harness the power of quantum mechanics is, well, it's really, really hard. The very weirdness that makes it so powerful also makes it unbelievably fragile. We're kind of facing a major stability crisis in building our quantum future.
So the soul of a quantum computer is something called a qubit, but the quantum information you store in these qubits is just so delicate. It's constantly threatened by this thing called decoherence, where the information just vanishes. It evaporates into thin air, making the computers unreliable and really holding back their insane potential.
But there's been another massive breakthrough. Get this, researchers at the Norwegian University of Science and Technology have figured out a new way to track this data loss, and it is a staggering 100 times faster than anything we had before. That is a total game changer for building quantum computers that actually work.
They can now figure out what's going wrong inside these super complex systems in just 10 milliseconds. For the quantum world, that is basically real time.
Being able to see the tiny little glitches that make information fade away as it's happening is an absolutely essential step toward finally building stable, useful quantum computers.
All right, so we've got atoms being in two places at once. We've got real-time diagnostics for quantum computers. So what? Why does this all matter? Well, it matters because both of these breakthroughs are pushing us, step by step, toward the single greatest goal in all of modern physics, what they call a theory of everything.
See, right now, physics is kind of a house divided against itself. On one side, you have Einstein's general relativity. It beautifully explains gravity, planets, galaxies, the really big stuff. On the other side, you have quantum mechanics, which perfectly describes the tiny subatomic world. The problem? The two theories are completely incompatible. Their math just doesn't work together. They hate each other.
So the holy grail, the ultimate prize, is to find one single, elegant mathematical framework, a master equation called a Lagrangian that unites both of them, a theory of everything. And by finally proving that particles with mass, particles affected by gravity, still obey these bizarre quantum rules, we are finally dragging gravity into the quantum playground. We're getting closer to finding the true mathematical blueprint of reality itself.
So, think about that. The solid world you see around you isn't really a world of single certainties. It's more like this buzzing, chaotic ocean of infinite possibilities, all constantly interfering with each other, until only the most efficient, the most probable path survives to become what you call reality. The principle of least action is running the whole show, which leaves us with one last, kind of chilling question. If the reality we experience is just the winner of a cosmic probability contest, what other realities are playing out in all those other paths that we just can't see?